Hello guys, today you are going to learn how to read the thermodynamics tables in the appendices. This is in the chapter 3 in my textbook called as Properties of Pure Substances. In this chapter, you're going to learn how to differentiate the state of the pure substances as in compressed liquid, saturated mixture, or superheated vapor. So first, I won't go through all the theory behind this. I'm going to only teaching you the steps on how to solve this question. Okay, here are some notes you need to know. To find out your properties, first you need to determine your state of your substance, either water or refrigerant. So to find out your state, you need two intensive properties. In this case, you can understand it as information. So it's either given or you find it. To define your state, you need pressure or temperature, or you can have specific volume or internal energy or enthalpy or entropy, or you can have quality if it's given or stated as a saturated mixture. All information here, you must have at least two to define your state. And one tip here is the mass cannot be helping at all because we only need intensive properties. Mass is something like extensive information, but mass and volume do contribute to specific volume, which is your V, and you can define your state with this. After that, second, for compressed liquid, all the information you can directly get from table or through some interpolation or approximation. For superheated vapor, you can get information from table or interpolation. If you have a saturated mixture, for example, you want to find a specific volume, you need to do some math, which is the specific volume at the saturated liquid plus the multiplication of the quality and the specific volume of the difference. I don't know how to say this. Difference of the specific volume between the saturated liquid and the saturated vapor, which is this formula if you need this. This will be very helpful. Also, in the same case, if you need to find the internal energy and the enthalpy for saturated mixture, you can use the formula, just substitute the V with the U, but the quality remains same plus. Also, you can use this equation to find out your quality if the internal energy of this state is given. Okay, now we're going through the example 1. So how do you solve example 1? Let us define the state. Do you have pressure? Yes. Do you have another intensive properties? Nope. Mass doesn't give you, volume doesn't give you, but the volume divided by mass give you specific volume. It will define your state. So pressure at 200 kilopascal and the specific volume is, press your calculator, 1.2 divided by 1.5, you get 0.8 meter cube per kilogram. Okay, so these two define your state. But is it compressed liquid or saturated mixture or superheated vapor? Don't worry, let us go to table. So this moment you will open your table. Don't worry, I will provide the link at the description below. So you go to table A5 first. Because pressure is given, so you go to pressure table and go to 200 kilopascal, as the question says. And then in this line, you need to compare your digit. Your specific volume found is 0.8. Apparently, it's in between the VF and the VG, meaning this is not compressed liquid if it's less than, and is not an superheated vapor if it's more than the VG, but it's in between, meaning it is an saturated mixture. So now you need another quality. Another property named quality, the X. Yeah, the X. You need another quality, the X. You need another quality, X. How do you find an X? Is equal to your specific volume minus specific volume as saturated liquid divided by the difference between the VG and the VF. And this is 0.8. This is for your table. This is also for your table. So pressing your calculator, you should get, try 0.001061 divided by the difference 0.88578 minus 0.001061. I get 0.9030. 0.9030. Okay, you find your another intensive property. Are you okay to find your H? Yes, you are. By using which formula? H equal to HF plus the quality times the difference between the Hg and the HF. So, do you have HF, HFG, and X? Yes, this is here. And then this is from table. This is also from table. So, how to read your table? You open your table. You look at the enthalpy here for the HF and HFG. So, your mathematical calculation should sound 504.71 plus 0.9030 times 2201.6. You should get 2492.7. 2492.75. If you round it off. So this is a final answer. This is how you got it. So now let us try to solve the way to find the properties if the state is in superheated vapor, which is our example 2. So question says find the internal energy, the U, of the water at a state where the pressure and the temperature is given. So before, assume we don't know the state. So let us go to table A4 or A5. I prefer F5 here since the digit is more approachable. So when you go to table F5, 7 megapascal is equivalent to 7,000, right? So here, and you look at the temperature. You see the temperature. Okay, and then you look at temperature is 2 at 5.83. Is it above? Is your temperature above this or below this? 460 is apparently above this, meaning if the temperature given is above your saturation temperature, meaning it is an superheated vapor. You can imagine the case like your water temperature is above your boiling point, meaning your water is boiling, superheated vapor. So after we know that this is superheated vapor, we proceed to the second step, which is find the properties. Okay, so you know this is a superheated vapor. Please go to table A6, superheated vapor. and looking for the appropriate pressure for 7 megapascal in pressure, which is here. Yeah. And you look at temperature here. It's 400 and 450, but your temperature is 460. It's in between here. If it's 450, you will be alright. That's directly up on the table. It will be easy case, but it's in between. So you need to perform a mathematics solution, which is called as interpolation. So how do you solve? How do you do the interpolation? It's actually quite easy. So let me grab my pencil tool. Okay, 3074.3 minus the U divided by what is given is temperature, so 500 minus 460 equal to the U minus the U at 450 degrees Celsius, 2979 divided by your current temperature minus the temperature in the table, 450. And do some algebra, you will get U equal to 299.998.1. This is how you solve it. Now let us proceed to example 3. In this case, the step of your substance is assumed as a compressed liquid. So let's define the state first. You are given the water at such temperature and such pressure, and looking for the internal energy. Because the state is given compressed liquid, so you can directly go to table A7. For compressed liquid water, you need to go to table A7, looking at this pressure and this temperature. So you can directly get your internal energy equal to 333.82. So let's write it down. 33.82. Okay. Another method to solve this is go to table A5, and I mean A4. Let us go to table A4. So why we can go to table A4 to find the internal energy of this compressed liquid? So you might be asking, either table A4 is for saturated mixture or the saturated liquid or vapor? Yes, it is indeed. But for compressed liquid, you can make an assumption where the internal energy is approximately equal to the internal energy of the saturated liquid at which is your temperature is 80 degrees Celsius. You can only make this assumption if this is a compressed liquid. So you must go to table A4 here and go to the internal energy, which is 334.97. 334.97. You can see those two answers are very similar, because this approximation will only work. This is a compressed liquid. The reason why we can do this assumption is because the temperature, if this is a compressed liquid, the properties won't change very big or very much with temperature. Now here are some examples extra for you. I'm going to show you the quick way to do this. So these are the tables, and there are 5 questions here, and each question are given 2 intensive properties for you to fill in another blank. So look at the first question. Since the quality is 0.6, what does this mean? This means that This is definitely a saturated mixture because it has some quality. Remember, the quality only applies to saturated liquid, mixture, and vapor. 0.0 for liquid, 1.0 for vapor, and whatever in between must be the mixture. So after this, we can directly go to the table F5. Table A5. We know that if something is in the saturated mixture, the temperature must be the saturation temperature, which is equal to 120.21 Celsius. And the internal energy is using the formula, which is energy is 504.5 plus 0.6 times 2024.6 1719.27. Yeah. So next step. So second problem, the temperature and the internal energy is given. So what should you do? Since two properties are given and temperature is a priority, please go to table A4. Please define your state again. So go to table A4. At 125 degrees Celsius, you look at the internal energy. Look at the digit. Is it between, more than, or less than the boundary? We can see it's in between, meaning this is also a saturated mixture. So the first priority here is the quality. But before that, the easier one is the pressure. We all know that if something is at a saturated mixture, given the temperature, the pressure must be the saturation pressure. So you go to table, look again at this temperature you found is 222.23 kilopascal. So how do you find the quality? Quality is nothing but the internal energy here minus the UF divide the whole thing divided by the UFG. So let me solve this for you. X equal to 1600 minus 524.83 divided by 200,955. I get 0.535, meaning 53.5% is vapor. So let us go to the next question. Given the pressure and the internal energy, what should you do? Go to table A5. Why A5? Because it's a pressure given. So you go to table A5, looking for 1000 kilopascal. You find your internal energy is more than the boundary, more than 2582, meaning if something is more than the UG, more than the saturated vapor, what do you think? It must be a superheated vapor. So for table A5, it helps you to determine your state. So you go to table A6 and looking at 1 megapascal, and you go to your internal. In this case, the X is not variable. I mean, not available because it's not saturated something. So you go to temperature. Here is 1000 megapascal, and the internal energy is 2950. So you do some interpolation by yourself. I'm not sure what, but I can guess it is something very close, some 395, I guess. But you can do interpolation by your own, but I'm lazy to do it. It's not my job. So let's proceed to next. Question D says your temperature and pressures. What do you do? Do you know which day it is? You don't know. Again, go to table A5. Table A5 because 500 kilopascal is a whole number. So you go to table A5. You're looking at the temperature. At this temperature is below your saturation temperature. What do you think? If the temperature given is below my boiling temperature, meaning this is still water, I still can drink it. So this is a compressed liquid. So let's go to table A7 first, compressed liquid. Oh no, table A7, the lowest pressure given is 5 megapascal, but here is 500 kilopascal. So what do you do? In the previous example, I show you how to do the approximation. So you go, again, you can go to table A4, must be A4, okay? Go to table A4. Look at this temperature 75. You can say the internal energy at this pressure and temperature is approximately equal to the internal energy at saturated liquid at this temperature, meaning UF equal to, the U equal to 313.99. Again, I repeat, the internal energy of this compressed liquid can be approximated to the internal energy at a saturated liquid of 75 degrees Celsius. So the X here is not available. So let's fill in this. This is, I forgot to fill in this, sorry. This is as previous. This is superheated vapor. And this is compressed liquid. So let's say, look at this digit. Given the pressure and the quality is 0. So do you think it will worse again? Yes. Why? Quality 0. Does it mean anything? Yes. It doesn't mean nothing. It means your saturation mixture, saturate, it means your property is exactly at a saturated liquid. 0 means all thing is a liquid. So this is saturated liquid. So so you can directly go to table A5 and fill in the blank. Okay, at A at 50 degrees kilopascal, find the temperature must be the saturation temperature, 172.94. While the internal energy is the UF. The internal energy at the saturated liquid, 731.00. If you like my channel, if you like this video, and if your teacher sucks not my teacher, sorry, then please hit the like button at the video below or hit the subscribe button. And thank you for watching this video. I like your support.